Hello everyone, good morning. So I'm here to give an update on the work I'm doing as part of the Traveling Collaboration. I'm a PhD student at the University of Manchester. I'm supervised by Professor Ben Sappers. We're searching for pulsars, specifically in supernova remnants and pulsar nebulae, and also some unidentified tera-electron volt sources too. So you probably know about TRAPM by now. We're a large survey project searching for pulsars with MeerKAT. We've had some Manchester-based talks from the Fermi group, and I'm specifically going to talk about everything that's in our paper, which was accepted on Monday and should be on the archive soon, so you can read about the details of our survey and also our initial discoveries, which I'll cover today. So here's where we are after 2 years, roughly 2 years of observations. So we've now targeted 79 sources, and we have found 2 new pulsars in them. Here's a breakdown by type of what we've observed. So the majority are just canonical radio supernova remnants. You can find them in the catalogue. But also, many of these will also have pulsar wind nebulae in them. But also, we have targeted a lot of candidates. It's been a significant portion of our search so far. And the reason for that is because this was one of the motivations for the survey. We've had a lot of candidates produced. So this is a histogram of new candidates that have been discovered over the years. So many of them have now been confirmed, but we have lots and lots to confirm here, because these surveys have all found very, very low surface brightness shells, particularly on the galactic plane. They've been very successful at that. Another motivation for the survey was we might make some interesting, might be able to find out interesting things about the pulsar population using our search, because we're going to be searching a lot of sources, so we have a large sample. So you might take all the targets we've searched and do a hand-wavy prediction of how many we might expect to find, given a number of targets. And if you assume that the targets don't discriminate based on there being evidence that a non-radio emitting neutron star is present, then you can include also the fraction that might have be a magnetar, the fraction that might be CCO, luminosity is in there as well, beaming fraction, and maybe some other things as well. So I've summarized things that we kind of know already based on some brilliant studies of these things. CCO is a bit more blurry, and also there might be other factors that we don't know, so like how prevalent is scattering in precluding our pulsar detections? Are there maybe some more black holes than we thought? We don't know, just some ideas. So another motivation was this fantastic sensitivity that's offered by MeerKAT. So here I'm showing our sensitivity, the black and the grey lines here, depending on how many dishes we use and how much gain we have, as a function of pulse period. So it's best really on this plot to make this plot to compare to non-targeted galactic plane searches. So there's some different ones here over the years. So you can see we're about normally 5 to 8 times more sensitive than Murray-Yang at Parkes, and only the fast galactic plane pulsar snapshot survey beats us. So we actually avoid where fast is observing completely, because we expect them to find the pulsars that we would find anyway. So the key is, in designing this survey, we wanted to stick with L-band and also use 4,000 channels. And the reason for this is balancing the spectral index of radio emission from pulsars with the sky temperature, and using L-band and 4,000 channels means we can have a robust sensitivity also at high dispersion measures. So for example, P-alpha with Arecibo lost a lot of sensitivity at low periods because of their channelization, for example. So since the talk I gave last year, we found a new pulsar in 1818. So here's some information that we have about it. Pulse profile at L-band, it has a precursor, it has a DM of 435 parsecs per cubic centimeter. It rotates every 573 milliseconds, so quite slow. And it's very, very faint. It was very low signal to noise in our searches, and it's actually got a luminosity similar to the fast pulsars. So even though they're more sensitive than us, we are still able to recover a lot of these pulsars that should be able to recover roughly the same luminosity. And this was also right on the galactic plane too. So we were searching this source here, G15.9 plus 0.2. And we were actually searching for the radio pulsations from the CCO that's in the middle of this, but we also searched the whole remnant as well. And we found the pulsar in this nearby beam here. As Miguel was describing yesterday, we can do signal to noise based localizations, because we actually managed to detect it in the 6 beams that were in a hexagon around. And so we got a nice 10 arcsecond localization instantly. So we were able to do some timing straight away, which is very, very useful. And from timing, we don't have a solution yet, but we can set an upper limit on the p-dot and a lower limit on the age. So it's very, very old pulsar, very, very faint. We don't think that it's related to this CCO or the supernova remnant. We think it's in the foreground. The DM suggests that it's in the foreground. So last year I presented this pulsar, J1831. We have an extra year's worth of data, so I can give some update. Here's what the pulse profile looks like. So this pulsar was discovered nestled in some plurionic X-ray emission that was discovered by Suzaku. And around this X-ray emission is this candidate supernova remnant, this faint shell here that was discovered by the Glow Star survey. Here's where we searched around this, and we found it quite centrally in these 4 beams, so we were able to get a signal to noise, localization. Now with 2 years of time data, we have a position that's 100 times more precise. So I'm just going to go quickly through this slide. Here is our timing solution that's in our paper, and here's the residuals that you get when you compare the times of arrivals with this solution. So the key things are the age is 55,000 years-ish, and this is the second slowest radio pulsar in a PWN galactic, I think. I think there might be a slower one in the LMC, I'm not sure. Here it is on the PP dot diagram. You can see it's adolescent. It's moved somewhat away from the bulk of the young pulsar population towards the canonical pulsars. So, what other evidence do we have that all these three sources are indeed connected and form one composite system? Well, we did a few calculations. So, in general, the morphology of the X-rays, the spatial overlap between these sources, and everything we've learned from the pulsar all match. So, for example, size, you can do a calculation, so the size should be about 15 parsecs across for the X-ray pulsar wind nebula. This makes sense if you think about pulsar wind nebula evolution. And the morphology is interesting, so it's actually offset. The pulsar is still quite central, but the wind nebula is quite offset from the center, and this makes sense if you consider the evolution of the shell expanding and the reverse shock moving inwards in a density gradient of the interstellar medium. This would make sense. This would make it similar to like the snail pulsar wind nebula, something like that, but slightly more evolved. Anything more to say? Yes, also more evidence for the reverse shock is that if you take the spin down power that we got from the timing solution, you compare it to the X-ray luminosity, you get this conversion range, this uncertainty mainly comes from the distance. And it's a little high for pulsars of a similar E-dot, but this makes sense if this system has been remagnetized by the arrival of the reverse shock. It increased the magnetization by 2 orders of magnitude, increased the efficiency of the wind in converted to X-rays. Anything to disprove the connection? Well, one might expect very high energy gamma rays to be emitted from this because it's become evolved enough, perhaps, that some particles can actually escape the interior and maybe emit some very high energy gamma rays. This is expected because these things called tera-electron halos have been discovered, and we think that's the final form. The pulsar wind nebula is starting to really dissipate now, and all these particles escape and form a very extended high energy source. We don't see any excess in Fermi or in Hess, but this like blob here is where the shell actually is, but it's not a catalog source. But hopefully maybe the CTA can be sensitive enough to detect something. So, looking ahead, we'll finish our survey. We'll have 125 sources searched-ish when we've finished. And this sample will be large enough that we can do a kind of population analysis of all the things that we've learned, and hopefully constrain some of the things that I've mentioned before. So in particular, I'm interested in the luminosity. So we don't really know how the luminosity distribution of pulsars, intrinsic luminosity behaves towards the very low end, because we're obviously biased, these pulsars are harder to find. So 2 things will help with this. Our analysis, we hope, and also we're looking closely at how many pulsars FAST is able to find in these systems, because they're also probing this region. Secondly, we're exploring using the S-band receiver to look at some more interesting sources like the pulsar wind nebula, where we definitely know that there is like an obvious pulsar there, and if they're right on the plane, and also maybe some of these glow star candidates that are very small, because we might just be missing pulsars due to scattering as well. Okay, so to summarise, we've searched 79 sources, we found 2 pulsars. If you exclude the one that's not related, our discovery rate is approaching 1%, so much lower than we initially thought, and lower if you just do a hand-wavy calculation. The other source is quite interesting. It could be a nice bridge between the evolution of pulsar nebulas from very young to quite old TeV halos. In a low peak velocity scenario, we think that the peak velocity is very, very small. And so in the future, we will do an analysis to try and learn as much as we can from what we've done by utilising the fact that we've done such a large sample very, very deep on these sources. So yes, thank you very much.
Thank you, James. You were very well within time, so we have lots of time for questions.
We haven't done special. This could be happening, yes. So if you also look at other targeted surveys that have happened in the past, they found the pulsars very quickly, and then subsequent surveys didn't find any new ones for like 20 years. So we were hoping to buck the trend really, but it's interesting that we're kind of still seeing the same thing, right? But yeah, we haven't finished yet. Maybe we'll find 10 pulsars in the next year, I don't know. But yeah, it's very interesting. It could be interesting if the luminosity distribution is like bimodal, very low, so maybe fast finds, I think it's found 1 in the supernova already, I'm not sure.
There's a thing that's clear. When you look at the PP dot diagram, each decade in age should have 10 times more pulsars, just from constant formation rate. And this doesn't, which means that obviously they fade with time.
Sure.
So it means that if you agree with that, then the young one should be in general quite bright, because of course there's a lot more E dot
Sure.
to power the radiation. So it's I'm saying this is not surprising.
Okay, but what I was also, we were hoping maybe to find far away pulsars on these very distant shells, and it's interesting that we're also not seeing those either. So again, then scattering comes into it, so maybe we can have a go with S-band. So yeah, but definitely interesting. Good question, actually. I'm not sure. I imagine that we would just start with radio pulsars, because one of the aims is to try to recreate what we have detected to compare with, you know, what if the design of our survey. What will change? Sorry.
Like the outcome of your, population synthesis.
Well, again, it's tricky because we will probably use things from the literature for those priors, and those things are based on what we already know often.
Okay.
So I can't say. Yeah, we will mainly be focusing on like birth rate stuff, because
I see.
Because this kind of stuff could be a big factor in preclusion of new sources. Because like Michael was saying yesterday, the birth rate is like way too big than it should be. So if you have a really high birth rate, why don't you see lots of sources, on pulsars, for example? So yeah.
One more question.
Often, yeah, we do have distances. The distances you can get them through a number of methods. I would say the brightness is probably one of the less reliable methods, actually, because the spread in surface brightness and diameter basically is extreme, so you can't really say much. That's why we didn't say here. But yeah, you can kind of guess what the DM might be. We tried to do that at the beginning, but our pipeline is quite good, so we were able to just search over a large range in DM anyway, so we didn't have to take care of all that.
Nice, thank you.
Thank you, James.
Thank you very much.